Hey, welcome back, guys. It's been a while since I've done AP Chemistry stuff, but I just noticed the AP 2006 AP Chemistry FRQ exam was released this today. So I was going to go over and solve these problems, and you guys could use it as a reference. All right, so let's get started. Question number one on the 2026 AP Chemistry FRQ. Student performs a calorimetry experiment with KCl. Part A, consider the K plus ion in KCl. Write the complete ground state electron configuration for the potassium ion. So that's kind of important, right? So I underlined that. So um, let's go in and do that. So I'm going to scroll over here. All right, so for question one, oh, sorry. Question one, part A. Um, just double check, right? Because we want to make sure this is my reference table. And I noticed that AP got a new reference table for 2026. All right, potassium is right there. It's actually one before argon, right? Sorry, come on. One before argon. So what does that mean? You can do it two ways. You can do the noble gas core notation, or you can just do it this the way. It's a 1, 2, 3, 4. Potassium is 4s1. So going over here, potassium plus would be one less electron. So that'll be 1s2, 2s2, 2p6, 3s2, 3p6. And you wouldn't write the 4s1 because obviously that would be for potassium, not for potassium plus. Or you could also write the argon core notation. Um, so that's the argon core electrons, and then you have 3s2, 3p6. Either way would be acceptable. And this was kind of really simple, wasn't it? Right? So let's move on. Um, to go to B, part 1B, which has a larger radius, the K plus ion or the K atom? Explain your reasoning using principles of atomic structure. So what is the difference between the two? The difference between the two is that the K potassium ion ends with its lone valence electron in the 4s suborbital, right? So you would first start your answer, your explanation with your answer, right? So you would say, and they ask which is the larger, so you write that potassium atom has a larger radii or radius than that of the potassium plus ion. Now it says to justify using atomic structure. So what is that? So we would say something like K plus, yeah, has 18 electrons and its valence ends at the 3p subshell, right? Whereas the potassium atom with its 19 electron has a valence subshell of 4s. So therefore, what we would say is K plus has fewer shells than that of the K atom. All right, so let's move on. So that's one and two, part A. Oh, I forgot to write that, right? Go back. You want to clearly define your answers. So, oh boy. Okay. So you want to say 1A, right? Part one and two, actually. So I mislabeled that. That's okay. So we're going to go to part B. Part B says student performs an experiment to determine the enthalpy of the solution. of the KCl. The student places water in a calorimeter, measures the initial temperature, adds KCl, and stirs until the KCl dissolves completely. The temperature is continually monitored during the experiment. Data from the experiments given below. So let's take a look. We got your mass of water. You got your mass of KCl, and you got your initial temperature, Ti, and you got TF. What do we notice? Immediately, even before we start continuing with the question, we notice that the temperature has dropped, right? So since the temperature has dropped, that the reaction has absorbed heat, right? So therefore, we're guessing it's endothermic. All right, so let's move on. By the way, I forgot to tell you the disclaimer. I don't have the answer key, right? Like everybody else. So please take my answers with a grain of salt. There could be mistakes. If there are, please feel free to, call it out or mention it in the comments. All right, so part B, describe how the student can use the temperature readings during the experiment to determine when the solution is complete. So our guess is that the temperature reduction happening is due to a thermodynamics phenomena that's happening as the reaction is the dissolution is happening, right? So like I said, our guess is that perhaps this is an endothermic reaction. So therefore, as more dissolution happens, what happens is that the temperature of water keeps going down. So obviously, the best way to think about this is that as the reaction proceeds, the temperature will decrease. So how do we know when it's complete? We would expect to see that there's no more change in the temperature. So let's go write that down. I'm going to quickly, though, fix my mistake here, which is the mislabeling, right? So this is going to be 1A, Roman numeral 1, and Roman numeral 2. And let's go to 1B. All right. So for 1B, what do we know? We know that the student can tell the end of the solution by, that's a B, seeing that there is no more change in the temperature of the reaction solution. Okay, and I think that about covers it. All right, so let's go back to C. Part C, what does it say? So B's done. That's what again, I used to tell my students when I used to teach AP, I used to tell students to put a check mark so you don't accidentally miss anything. Let's go to C. Use the data in the table to do the following. Calculate the magnitude of thermal energy in Q in joules transferred during the dissolution. So I'm already thinking Q is equal MCAT, right? Maybe. Calculate the value of the molar enthalpy of the solution or the heat of solution in kilojoules per mole. So let's go take care of this one first. So part C1. So I'm going to scroll down here and go to, let me just make sure that I have enough room. Yeah, that's enough room, right? So it's 1C, Roman number 1. All right, so what are they asking us? I want to leave one of the other things I tell my students, leave the first line blank and come back and write the question when you're done. They want the Q, all right? So I'm going to go here and write down Q is equal to, and leave it blank. And let's get going. So the equation that we need is Q equals MCAT. All right, now we have to be careful, see where the values are. Now, when you go back to this question, what do we know? Well, it says magnetic thermal energy transfer during the dissolution. Assume the solution has a specific heat capacity, right? So since it's a solution that we're talking about, right? So we would say we would have to use probably the mass, right, of let's see, both, right? Because this we have mass of water and KCl. If they gave you a heat capacity of 4.84 joules per gram degree Celsius, then you would assume that that's water. So in that case, we just use mass of the water. But in this case, it specifically says solution. So therefore, we're going to use the mass of both. So it's 97.5 plus 6.8. All right, so I'm going to try to hopefully remember that as I scroll here. So we know the mass is going to be, I think 97 point, I'm going to zoom in here. Zoom in. Okay. 97.5 grams plus our potassium chloride is 6.80. Okay. Our specific heat capacity that gave us is specific, right? And it's 3.95, I believe, right? Joules per gram degree Celsius. And what is our delta T? Our delta T was 21.1 was our final, right? And then 24.5 was our initial. So it's always going to be TF minus T initial, right? So therefore, it's going to be 21.1 degrees Celsius minus 24.5 degrees Celsius. What does that give us? Ooh, I don't know. Could I do this in my head? 8, 9, 10, 3. That's going to be 104.3, right? Times 3.95 joules per gram degree Celsius. And our delta T is going to be negative 3.4, I think, right? Like that. And what does that get us? Let me grab a calculator real quickly. Sorry, like I said, this is the first time I'm seeing these problems. So I get 104.3 times 3.95 times negative 3.4. And I get a value of negative 1400, right? Negative 1400, and that's in joules, right? So you can write that, or let's just quickly double check our sig figs, yeah? So let's go back. Looking at our sig figs, I'm guessing 3, right? So if we go back here, you see 3, 3, 3, 3. I don't, and then the specific heat capacity is 3 as well. So I'm going to assume that my sig figs, they're all going to be 3 because they're all multiplicative, right? So therefore, I'm going to say the answer is negative 1.40 kilojoules. Okay. So what I could do is go over here and just write down that since they asked the magnitude of thermal energy transferred during the dissolution, I would say, and they're asking for how much is transferred, right? So since it's how much transferred, it would say 1.4 kilojoules of energy is transferred. All right, let's go to Roman numeral 2. What does the Roman numeral 2 ask of us? Roman numeral 2 says, so that's check, calculate the value of the molar enthalpy of solution in kilojoules per mole for KCl, given that 0.0912 moles of KCl was dissolved. So that's the amount that was dissolved to get us that 1.4 kilojoules, right? Show the work that leads to your answer, include the sign with your answer. All right. Oh, that's nice of them. They used to not do that. Talk about science and just be like, gotcha. Right. So this is part 2. All right. So what are we doing in this one? Well, it says that what was the total amount of mass of the KCl? The total amount of KCl, right? Again, I'm going to skip a line here, is 6.80 grams, I think, right, of KCl, right? So what does that mean? Let's convert that to moles, right? So that is, what is KCl? Well, let's go check. Potassium is 39.1 and Cl is 35.45. So 39.1 and 35.45, that comes out to 74.55 grams per 1 mole of KCl. That gets us molar KCl. Now you can do this as a long dimensional analysis. That's perfectly fine too, right? But I will break it up so that it's easier for you to understand what's going on. So that gives me 0.0, the calculator. 6.8 divided by 6.8 divided by 74.55. That gives a 0.09. Hey, Mr. Kim, how did you know that it was going to be 0.0? Well, hello, it's 6 or 7 divided by 74. Of course, it's going to be a small number. All right, so I get 0. Sig fig says 3 sig figs, 0.0912. 912 and is the number of moles of KCl, right, that has reacted, right? Am I doing this right? 74, 6.80. Is that correct? Yes. All right, so now what? Now we're going to look at what's going on, and it's going to be the total energy those, and what do they want? They want kilojoules per mole, right? So therefore, what do we know? We know that the total energy was 1.40 kilojoules, right, per mole. I'm sorry, not per mole. Those just kilojoules, right? Total reaction. And we know that this was a product of 0. Can I get a 0, please? 0.0912 moles of our KCl. Right? So what does that come out to? 1.4 divided by, yes, sir, please. I get 15.348. Once again, 3 sig figs, that will make this 15.3. 15.3 kilojoules. All right, so going back to the question, it says, calculate the value of molar enthalpy. So we would say delta H of the reaction is equal to 15.3 kilojoules. And I probably want to box that in. Okay. Page 1 looks okay. All right, so let's go back. Part 2 is done. Let's go to part D. Calorimeter is not perfectly insulated. Would this cause the magnitude of the delta H calculated in part 2C to be greater than, less than, or equal to the accepted value? Well, let's think about that. So if there's no insulation, what happens? We have heat loss, right? Heat loss equates to what? We think reaction made less heat, right? In terms of energy, right? So our Q value that we think is happening is going to be low, right? So what are they asking? Calculate in part. So we would think that'd be less, right? So let's go fill that out, right? So 1D, question 1D, all right? It says, what would we say? It says, would it be greater, less than, or equal? So we would want to start with the opening statement, which is answering the question, which would say, we would, delta H of the reaction would be less, comma, because due to poor insulation, sorry about my handwriting, we would have heat loss, right? So due to the heat loss, so we would think the reaction produced less heat per mole than actual. Okay. All right. So let's go to D. Where's D's done? Let's go to E. This is a long one, right? All right, the student performs a second experiment using the same mass of water, but 6.80 grams of rubidium chloride instead of 6.80 grams of calcium chloride. Magnitude of the molar enthalpy solution of approximately equal. So what does that mean? That means, let's go for a second and take a peek look. All right. Rubidium versus potassium. So what's going on? Rubidium is a lot heavier, right? So it's more massive. In fact, it's more than twice the mass of potassium. So we would expect that here the mass of rubidium chloride is greatly larger than the mass of potassium chloride. All right. So what does that mean? That means since we're using the same amount of mass, what does this translate to? This translates to the fact that in this reaction with 6.8 grams of KCl versus RBCl, right? Rubidium chloride would, because think about this, right? So you're going to take your the molar mass, right? And you're going to divide 6.8 by the respective molar masses to get your moles, right? So what does that mean? If you're in the rubidium chloride situation, you're taking 6.80 and you're dividing by the molar mass of rubidium chloride, which is much larger. So since you're dividing 6.80 by a much larger number, we'd expect the moles of rubidium chloride to be a lot smaller than the mole of our KCl, right? So what does that mean? That means uh, less number of moles, but what did they say? They said the molar enthalpy of solution, meaning the number of kilojoules per mole, turned out to be exactly the same or approximately the same. So that means what? The total amount of energy or Q that was produced by either rubidium chloride or KCl was exactly the same. But in the case of rubidium chloride, it's less number of moles that produce the same amount of heat. So what does that mean? That means, a mole per mole, it's got more punch, more energy, right? So, what are they asking us now? So, is the magnitude of delta T in the rubidium chloride experiment greater than, less than, or equal? So, what is delta T again? Delta T, as we calculated earlier, was the amount of kilojoules per mole, right? That we're looking at. So, they're asking you, mole per mole, does rubidium chloride have more energy or less energy? And we said clearly here, rubidium is less number of moles, right? But it's producing the same amount of energy, which means that mole per mole, it's got a greater kilojoules. Or if you want to just talk in terms of algebra, you would be dividing the same number of kilojoules by a smaller n on this side. Therefore, what happens? You would have a larger value, right? Um, so let's go and say that part 1E. So in 1E, you would say rubidium. So I'm gonna say start with the answer, right? The answer. They're asking us what? Magnitude. So magnitude of delta T in rubidium chloride will be larger. Rubidium chloride has a larger molar mass, right? Than KCl, right? Therefore, equivalent 6.80 grams will give us smaller number of moles of rubidium chloride than moles of KCl. Since less moles of rubidium chloride gives rise to similar heat. It's a heat, right? the molar enthalpy, right? Similar molar enthalpy or molar heat. It must mean rubidium chloride has larger kilojoules per mole. All right, let's keep going. So that's E. All right, so E's done. That's good. Let's go to F. F is got 3 parts. It says rubidium chloride has a KSP. All right, here we go. So this is where you're going to actually start putting on your equilibrium hat, right? And that means, what does that mean? When I used to teach AP, I used to tell students that whenever you see something like KSP, all of a sudden you got to put on your equilibrium hat. That means that you're going to start thinking about some of the vocabulary that you need to know in order to do the equilibrium. All right, so let's go back. So it says write the net ionic. Oh, that's really easy, right? It's simple ionic. So I don't know about you guys, right? This test so far, it's stupid simple. I'm sorry, right? I think this is one of the easiest chemistry FRQ I've seen. Okay. They want rubidium chloride net ionic equation. What does that mean? That means there's nothing to write. It's in water, right? So it's going to be rubidium chloride, solid, um, undergoing dissolution, and you're going to end up with rubidium, which is a group 1, right? So it's going to be this plus chloride, which is that. That's it. It's that easy, right? My regions they can do this. Some of them could do this. Few of them, whatever. All right, so we did that. Calculate the molar solubility of rubidium chloride, right? In a saturated solution at 20 degrees Celsius. So saturated, we're at equilibrium, right? So what at EQ? Show the work that leads to your answer. Let's go get this done. All right, so this is going to be part 1F, Roman numeral 2, right? Make sure I have enough space. Sure I do. So I'm going to go to Roman numeral 2. That's terrible. God, you can do better than that. I'm sorry. Here, 2. All right. So to calculate this, what do we got going? We have their what are they asking for? Molar solubility. All right. So they're asking for molar solubility, which is what? Which is the rubidium, right? In this case, it's this because why? Um, it's the Van Hoff factor is 1, right? I'm sorry, no, Van Hoff factor. Sorry, wow. Van Hoff factor is 2, right? Which means that it's just it's a single cation and single anion that's coming apart. So the concentration of ions, any ions, would be equivalent to the molar solubility. All right. All right, so if you don't know, go back to your notes. If you don't have in your notes, I don't know, ask your teacher. I don't care. It doesn't matter. All right, so going back to this, what do we got? We got rubidium chloride. We got the equation up here. I'm going to just rewrite it. You don't have to, right, in the actual test, but I'm just trying to explain this to you guys, right? So you got one of these, right? So what's going on? KSP is going to be what? Our KSP expression is special because it's going to be only the solubility product, right? Product side. So it's going to be RB plus and Cl minus like that, right? So what? Well, now we know that because it's a 1-to-1 ratio, right? This value here is going to be equivalent to x times x, right? Or equal to x squared, which is equal to our KSP, right? What do we know? KSP is given to us. Let me just scroll up there real quickly and look at it. I should have looked at it before I came down here. Our KSP is 57, right? So you go here, and we know that our KSP value was 57, right? Hello, right? So therefore, what do we know? X squared is equal to 57. Right? Therefore, x is equal to the root of 57. And that I cannot do in my head. So what is that? That comes out to 7.549. I believe sig figs is what? 2, right? 50, no, KSP was 57. All right, so I'm going to stick to 2 sig figs. It's going to be 7.5. 7.5 molar. And we know that this is equivalent to RB plus, and it's also equal to our Cl minus, which also happens to be our molar absorptivity. So we know that it's going to be 7.5 molar. Don't forget your units, box it, and we are done with 1F2. All right, 1F2 is done. All right, so look at second saturated solution is prepared by dissolving rubidium chloride in 1 molar KCl. Oh, right away, what am I thinking, right? KCl, what's that, right? Think about that, right? All right, fine, I'll tell you. Common ion, right? Remember common ions? All right, so rubidium chloride and KCl at 20 degrees Celsius instead of in pure water. Will the molar solubility of rubidium chloride in 1 molar KCl be greater, less than, or equal to the solubility in part F2? My gosh, is this test easy? What are they? They didn't even ask you to calculate anything. This is stupid. All right. So I don't know about you guys. If I were taking this, I would have been like, oh, this test is simple, right? It's 1F3. They're not even asking to calculate. They're asking you, hey, if you're trying to dissociate rubidium chloride in a solution that already has KCl, which we know it's group 1, it's completely soluble, it already has Cl minus, right? So therefore, they're going to ask you, is it going to be greater or less than? So part 3, right? You would expect it to be what? Less, right? Because you got chloride on the product side. So, but I'm going to leave it out in case you don't understand what I'm talking about, right? So I'm going to write that since I'm going to give the explanation. KCl dissociation releases Cl minus, a common ion, to RbCl dissociation. We would expect to have increased concentration of Cl minus, which is on the product side of RbCl dissolution, right? Therefore, we expect the presence of Cl minus to drive the reaction to the left solid, right? So what does that mean? So we would say, it said, would you expect the solubility? So we say the molar solubility would be less. Okay, done. All right, we are done, I think, with question 1. I'm going to take a pause here, right? Because I want to break it up into different videos. All right, so here we go. So this is question 1, and I hope this was helpful. Thank you for watching, and I will see you on the next video.